So when the change in energy is greater than zero, we actually call that an explosion. So let's look at these one at a time. So the elastic collision is easiest to understand, I think. So for elastic collisions, we have two objects. They're coming in fast. And post collision, they go away from each other with exactly the same speed as they started with. So they just bounce off each other and go on their merry ways. The reason why we call it elastic is because at the moment of collision, you're going to get some deformation. So instead of a perfect ball, you might have like a flattened side, and the other ball also has a flattened side. But when the collision is over, they spring back into their original shapes elastically. Another way of thinking about it is that the objects are briefly behaving like springs during the collision. So all of the kinetic energy gets briefly stored as spring energy and then released again as kinetic energy as they spring apart. Inelastic collisions we have the balls coming together and deforming on collision. And when they spring apart, they're still not quite right. There's some permanent damage to the object that happens in an inelastic collision. And some of the kinetic energy that the objects possessed before the collision goes into breaking the objects. Um, in a completely inelastic collision, instead of the balls bouncing back and going their merry ways, we actually see them stick together. We have one ball and another ball, and they are together, moving with the same velocity. That's where the maximum loss of kinetic energy occurs. So these elastic and inelastic, these are models for collisions. So no collision is actually perfectly elastic or perfectly inelastic. In the real world, it's one of the many jobs of a material engineer is to measure the coefficient of restitution. Right? The coefficient of restitution is the ratio of kinetic energies before and after a collision. It's the kinetic energy after the collision divided by the kinetic energy before the collision. For a perfectly elastic collision, this is just 1. 100% of the kinetic energy is preserved. For all real collisions, this will be some number between 0 and 1. That leaves just one type of collision, which, as I said, is an explosion. In an explosion, we might have one object going on its merry way, and then we convert some chemical energy into kinetic energy. And instead of one object, we have multiple objects flying off in various directions. Do you have any questions about this sort of division of collision types? Yeah, like a firework, exactly. So a firework, goes up, it explodes at the top, and the pieces of the firework, put together, have more kinetic energy than the firework did overall beforehand. Calderon, they just get smaller and smaller. I'm not sure what you mean there. Can you clarify? If you explode the same ball when it doesn't stop getting small, well, presumably there's only one explosion happening at a time. So, right, but from a physics point of view, what an explosion does is it takes an object, turns it into smaller objects, and increases the overall kinetic energy of the system. But just like in real life, cool physicists still don't look at explosions. Also, no matter what type of collision it is, uh, you're still going to use the same momentum analysis. The only difference is, like, sometimes you can actually use energy analysis as well. So you can get more information about the system by analyzing it once with momentum, analyzing it once with energy, uh, and then combining the two. So that's why even if collisions aren't perfectly elastic, we'll end up modeling them as perfectly elastic because that lets us use conservation of energy as well as conservation of momentum. And we'll do a problem like that before the class is over. I do want to make note of a couple of smaller concepts before we completely move on. I want to talk about the center of mass of an object. Up to this point in the class, we have treated all objects kind of implicitly as having no size. All of their mass is in exactly one point, and forces are directed exactly onto that point. Of course, that's not realistic. In the real world, we have extended objects, right? Objects that have dimension, they have length, they have height, they have breadth. And considering the center of mass of an object is our first attempt at kind of dealing with that fact. So the center of mass has a, well, first we'll talk about how to calculate it. Because the center of mass of an object is kind of it's a weighted average of where the mass in an object is. So when we calculate the center of mass, we're going to end up getting like an average position for for the mass. So what we're going to say is we're going to take this, we're going to define this moment arm. So we're going to weight the position of each piece of mass in an object by how much mass there is at that point, and also how far it is from the origin. If we add up all of these and we divide by the total amount of mass in the object, then we will have given ourselves an average position of the mass. Now, if instead of, so this formulation kind of assumes that we have like some discrete bits of mass. So maybe if we had if we were analyzing the movement of a carbon tetrachloride molecule, we would be able to say that there's a carbon molecule in the center, and there are carbon atom at the center, 4 chlorine atoms surrounding it. And it's a pretty good approximation to say that all of the mass in the object resides at 5 points, right? 1 point for the carbon, 1 point for each chloride. And that would be a perfectly legitimate way of getting the center of mass is to assume that each individual atom has no size, but instead is just a point with all of its mass at one location, and then average over all of that. But we don't have to restrict ourselves to situations in which the mass is discretely distributed throughout an object. We can also talk about real objects. So if we have, say we want to know, well, what is the center of mass of an I-beam? Which is kind of an important thing to know if you are doing some structural engineering. Also pretend that I can draw an I-beam. So for a continuous mass distribution, we can do the same thing, but we can write it in terms of an integral. So we can write down an integral in some way that catches all of the mass and then divide by the total mass. Does anyone have any questions on these two definitions so far? Now, why do we care to find the center of mass of objects? Because all of the tools that we have learned so far, right? So Newton's second law, right? Conservation of energy, conservation of momentum, right? Kinematics. These don't just apply to point particles, right? These all apply to center of mass analysis. That is, we can, even though we know that the mass is spread out, once we know where the center of mass is located, we can apply all these tools as if all of the mass was located at the center of mass. and our tools will work perfectly fine. In fact, the book goes into some detail to show that, in fact, if you apply, for example, Newton's second law to the center of mass of an object, you don't get just approximately the same answer as applying Newton's second law to each individual chunk of mass. You get exactly the same answer. So once we know the center of mass of an object, we can treat it as a point mass and apply all of the tools that we have learned to it. Any questions on center of mass? So the last thing that I want to talk about today is something near and dear to my heart, and that's rockets. Anyone else like rockets? Think space is awesome? I imagine that in a room full of engineers, I'm going to get 100% yeses to that question. I think that's why we're here. Yep. That's why I started studying physics too. By the way, there's this great YouTube channel. First of all, I mean, all of you should be playing Kerbal Space Program in your spare time. But there's this great YouTube channel that does a segment called Space This Week, and just focuses on all of the space launches that happened in the last week. It's very instructive, and if you're interested in space launches at all, you should keep up with what we're doing in space. So, when we formulated our idea of momentum, we started by saying, well, force equals a mass times a change in velocity. Right? And then we defined, like we said, well, we can take, since m's a constant, we can take it inside this derivative. So it's the derivative of mv dt. And we say, well, mv is this thing we're going to call momentum. We're going to rename that quantity. And when we got there, we got there by assuming that the mass of an object is constant. However, that is not necessarily true, and it is definitely not true for rockets. So the way a rocket works is by taking part of its mass and throwing it out the back at really high speeds. So we know that momentum has to be conserved. So we can write down some relationship and say, well, the net change in momentum has got to be 0. And that's got to be equal to the change in momentum of the rocket plus the change in momentum of the exhaust. Since these are the only two momentum changes we're looking at, we can say, well, the change in momentum of the rocket, let me actually use capital R here. It's got to be equal and opposite to the change in momentum of the exhaust. That is, if you throw something out the back at high speeds, that's going to move you forward. As anyone who has ever tried to play catch on a rowboat can attest. All right. So now we analyze in a little more depth what is the change in momentum of the rocket at a specific point in time. Like, so for over a very short amount of time, we might say that the rocket has some mass but loses a bit, and the rocket has some velocity but gains a bit. Likewise, in a small amount of time, we throw a small amount of exhaust out the back, and it experiences a velocity change equal to v the rocket minus the exhaust velocity. Okay, so now we do some expansion. So we've got two binomials on the left-hand side. We're going to FOIL those out. So we get mass of the rocket, velocity of the rocket, plus mass of the rocket, change in velocity of the rocket, minus change in mass of the rocket, velocity of the rocket, minus change in mass of the rocket, change in velocity of the rocket, equals change in mass, like the mass exhaust rate times the rocket velocity, minus the exhaust mass rate times the exhaust velocity. Is everyone with me so far? So now we're going to do something that physicists do from time to time. We say, well, dm is small and dv is small. So dm dv, that's super small. In fact, it's so small we might as well say it's 0. So we're just going to totally ignore this term. We're also going to note that the small mass of the exhaust and the amount that the rocket mass changes by moment to moment, those are the same. So the mass gained by the exhaust is the same as the mass lost by the rocket. So let's do some collection. So the very first term is mrvr. That was the old momentum of the rocket, plus mr dvr minus dmr vr. And on the other side, instead of dm, like the mass of the exhaust, we're going to write minus the mass of the rocket. And the same, we're going to replace this minus differential mass of the exhaust with a positive differential mass of the rocket. Notice we have a dmv on both sides, so we can go ahead and cancel that. So we have mr, vr, okay. So at this point, what I would like to do is actually, we don't want to consider the original momentum. We just want to consider the amount by which it changes moment to moment. So we're going to for the moment, we're going to ignore this term, which is the original momentum of the rocket. And I lost my train of thought. Oh, that's right. So I'm going to drop the subscripts as well. The subscripts on the mass, because they're the same. So we have m dvr equals exhaust velocity dme. So the change in the momentum of the rocket is equal to the change in momentum of the exhaust. I mean, that's what we started with, but this gives us some power because we're getting toward a something something nice here. So what we're going to do is we're going to put the rocket velocity by itself on one side of the equation, and we're going to put everything else on the other side of the equation. So I'm going to give us a little space for that. All right. Now we're going to integrate both sides. So what do we get when we integrate the left side there? Like, what do we get when we integrate dv from v naught to v final? Close, Josue, not just v, but delta v, right? Because v final minus v naught, that's just what we mean by delta v. And on the right-hand side, what do we get? What do we get when we integrate dm over m? Nobody wants to do that? Right? What's the... You guys just had calculus last semester. log delta m. Eric, you're real close. So you get VE times log of MF minus log of M initial and we remember our rules of logarithms, right? So the difference of two logs is the log of the product. Now, throughout this derivation, I've kind of implicitly assumed that there's a negative sign inside the exhaust velocity because it's going the opposite direction of the rocket. But it's more usual to see this written in terms of like absolute values. So we want the the speed of v. So there's a negative sign inside v because it's going because VE is in the opposite direction of delta V. But we can take that negative sign inside the log and use it to switch the numerator and denominator of that ratio. And so it's more usual to see something like this, like the speed of the exhaust rather than the velocity is equal to log and then log of m0 over mf. Okay. This is what's known as the Tsiolkovsky rocket equation. What's on the left is delta V. What's on the right is just rocket characteristics. So the exhaust velocity depends entirely on the design of your rocket engine, and the ratio m0 over mf is entirely dependent on what fraction of your rocket is payload and what fraction of it is fuel. How do you spell that? It's Konstantin Tsiolkovsky. So Tsiolkovsky. Let me write that down. Wow, and I just misspelled it, even though I just said it. This is the basis for any launch planning that you might do. So does this mean you can be a rocket scientist now? I certainly recommend you try. Right? Like there's definitely more to rocket science than this, but other than this, it's really an engineering problem. So I know that's a pretty I guess snide answer from a physicist, but so I want to show you all an image. When we talk about how far space is away, it's actually not that far away. You know, space, the International Space Station orbits at about 400 kilometers of altitude. So it's closer than San Francisco. So the space is closer than the Pacific Ocean if you live in Las Vegas. What space is fast away. So this is a kind of cool like subway style map of the solar system. And what this tells you is how much delta V you need to get to various places in the solar system. So for example, when you are doing a planning just to get from Earth's surface into low Earth orbit, which is where satellites go, you need 9,400 meters a second of delta V. What does that mean? Well, it's the rocket equation we just saw. You need to design your rocket with a payload fraction and an exhaust velocity such that the total delta V it's capable of is 9,400 meters a second. So this is how we measure how far away things are in the solar system. So getting from Earth to low Earth orbit is only 9,400 meters a second of delta V. And then getting all the way into moon orbit is only another 4,000. So it's frequently said that if you're in Earth orbit, you are halfway to anywhere in the solar system. And from a delta V perspective, that is certainly true. Yeah, so that's what it means if, say, you need more delta V. And so even though delta V is literally a velocity, it's frequently useful to talk about that distances in the solar system in terms of how much, right? How much delta V you need to get there. All right. Any questions on this material? Why does it take so much to get out of Earth? It's we're at the bottom of a gravity well. So that 9,400, and by the way, that 9,400 um, doesn't include air resistance. So that's just how much work it takes to change your gravitational potential energy to get up to 250 kilometers of orbit, and also to increase your linear speed by enough so that you can actually orbit at 250 kilometers up rather than hopping up and falling down. So just to orbit at low Earth altitude, low altitude orbits, you need a horizontal speed of about 8,000 meters a second. That's what it takes to have a stable orbit in low Earth atmosphere. Would returning have the same delta V as it takes to get anywhere? No, actually, returning from Earth orbit is basically free. In fact, you have to work to get rid of your velocity so that you don't crash and die. Sometimes we call that lithobraking, and it is not recommended for manned flights. So I do want to do one problem together before we adjourn for the day. I also want to make a bookkeeping note. We plan before a break. We talked about having our second exam next Wednesday. And as far as I'm concerned, that's still on. So next Wednesday, we'll have an exam and it'll cover energetics and momentum. Okay. So let's do number 104 from the book. So here's the idea. You've got two billiard balls that are at rest touching each other. And pretend that I drew these so that they lined up. There we go. We have a third ball, the cue ball, which for some reason is much larger than the other balls, but we'll go with it for the moment. It strikes both balls at the same time. We know what the initial velocity of the cue ball was. It's just 3.8 meters a second in what we'll call the x direction. So x direction is this way, y direction is this way. We would like to know what is the final velocity of all three balls. So first we have to do a little bit of geometry. So all three balls are the same size despite what I've drawn. It's a radius there. Right, a radius there. A radius there. So question 1, like sub-question 1, at what angle does the cue strike the other balls? Somebody pipe up. So let's see, we've got some little bit of trigonometry to do. Who can figure out what that angle is? Pi over 6? Yep. That's exactly right. And we know that because the hypotenuse is a length 2r, the opposite side is a length 1r. So we can say, well, sine of the angle then is equal to r over 2r, which is a half. And that implies that theta is pi over 6. Good job, Drain Master. So that's the angle. And because, well, you know, we'll write it as pi over 6. But note that this is all, I would also have accepted 30 degrees. Okay. So, sub-question 2, what's the initial velocity in the y direction, or what's the initial momentum in the y direction? Good job, Keys. It's 0. There's originally no velocity in the y direction, which means no momentum in the y direction. But then what does that say about the final momentum in the y direction? So what will be the momentum in the y direction after this collision of billiard balls? Hmm. So are there any if our system here, our system is all three balls. Are there any external forces on this system? Right? Like we're not considering any external forces here. We haven't described any. So if the external forces are 0, that implies no change in momentum. Which means if the initial momentum in the y direction is 0, so is the final momentum in the y direction. So the y momentum at time A is 0, therefore the y momentum at time B is 0. Let's actually give ourselves some room to analyze this bit for a moment. If that is so, let's actually spend a moment writing down what the final velocity, the post collision velocity for ball 2 and ball 3 are going to be. So ball 2 is going to have some total velocity. We don't know what it is. But in the x direction, we're going to get cosine pi over 6, and in the y direction, sine of pi over 6. Right? Because we know that it was struck at an angle of pi over 6, so whatever velocity it acquires, the x part has got to be the cosine, and the y part's got to be sine. Now the third ball is almost the same. It's also going to go in the positive x direction because it was struck from the left. However, it was also struck from the top, so it's going to go in the negative y direction, we expect. Since we know already, oh, and I guess for completeness' sake, the first ball, we expect it's just going to go in the, it's going to bounce off to the left. It's not going to bounce in the y direction because it's struck balls equally above and below it, so those forces on it are going to cancel out. Since we already decided that our net momentum in the y direction has got to be 0, that means that VB2 sine pi over 6 minus VB3 sine of pi over 6 have to equal 0. But this can only happen if VB2 is equal to VB3. So there we go. So considering the y direction tells us that the two balls that are struck by the cue are going to end up with equal momentum. Any questions so far? Right, just for completeness, this is ball 1, ball 2, ball 3. Okay. Could I go back for a sec? Yep. To this page, McHenry? Okay. You have any? Did you have a question on this page, or did you just need to copy some stuff? Okay, excellent. So we've considered what the angle of impact is. We've considered what happens in the y direction. So now we need to consider what happens in the x direction. So in the x direction, we still have conservation of momentum, right? So we don't have any external forces, which means we don't have any changes in momentum, which means that the x momentum before the collision has to equal the x momentum after the collision. So before the collision, we've got only ball 1 moving. So there's the momentum prior to the collision. After the collision, we have mvb1. So we expect that the first ball is still going to retain some velocity. We have the x velocity of the second ball. And actually, since we determined that the velocities of ball 2 and 3 after the collision were equal, we can actually just slap a 2 in here, right? Because there's two balls, each with the same momentum in the x direction. There's a mass in every single one of these terms, so it's going to cancel out. So we have VA1 equals VB1 plus 2 VB2 cosine pi over 6. Now, we know what the initial velocity of the first ball is. But we don't know VB1 or VB2. That's two unknowns. We can't solve for that using just momentum, right? Because we're out of things to try. We've tried the x direction, we've tried the y direction. That's all we've got. So it's at this point we need to use the fact that billiard balls have elastic collisions. and also that collisions only has one s. Since they have elastic collisions, we have not just momentum conservation, but we have energy conservation from before to after the collision. So we can also write down what the energy prior to the collision and the energy after the collision has got to be. So before the collision, we have just the kinetic energy of the first ball, of the cue ball. After the collision, we have the kinetic energy of the post-collision kinetic energy of the first ball. We also have the kinetic energy of the two non-cue balls, which are traveling at the same speed. So there's two of them, and each of them has 1/2 mvb2 squared worth of kinetic energy. All right, there's a 1/2 m in each one of these terms. They cancel out. And I'm going to go ahead and move everything to the right-hand side of this equation. Okay. Now here we have another equation with the same unknowns as we got when we analyzed the situation using momentum. So what can we do? Like how do we finish this up? We can solve for VB1 and using the momentum observations. So VB1 equals VA1 minus 2 VB2 cosine pi over 6. And then that can get plugged in over here. So we get 0 equals minus VA1 squared plus VA1 minus 2 VB2 cosine pi over 6, quantity squared. Expand out that binomial, and we get VA1 squared plus 4 VB2 squared cosine squared pi over 6 minus 4 VB2 VA1 cosine pi over 6, and then also plus a 2 VB2 squared from above. Our VA1 squareds cancel, which is nice. And then we're left with this seeming pile of garbage. But we're going to collect these. We have two terms with a VB2 squared in them. I'm going to go ahead and factor that out. So VB2 squared, 2 plus 4 cosine squared pi over 6 minus VB2, right, minus this linear term. And we're running out of time, so I'm not going to finish up the algebra, but we only have VB2 squared as an unknown. We can totally solve for it. Anybody think that they couldn't finish this analysis up? So this is all I've got for today. So if you want to see either this problem finished up or you want to see the solution to the quiz problem, feel free to stick around and we'll do that. Otherwise, y'all are free to go, and I will see you on Monday.